So, remember the early days of self-driving car hype? It felt like it was just around the corner, right?
Oh, absolutely. Yeah. Predictions everywhere. Robo-taxes, widespread adoption, maybe even by now,
Yeah.
mid-2020s.
The vision was definitely powerful. Those early demos looked, well, incredibly promising.
They did.
Yeah.
But the reality, it's turned out, and our sources are pretty blunt here, much more complicated than automotive experts realized at the outset.
Yeah, you see that. We've seen major companies kind of hit pause, delay timelines, some even sell off autonomous divisions and revamp their approach.
Which all points to a more gradual path than anyone really expected back then.
And that complexity, it really seems to boil down to two massive challenges, doesn't it?
It does. First, just dealing with the sheer real-world complexity and edge case complexity. I mean, the absolute chaos of everyday streets.
Mm-hmm.
And second, this absolutely critical need to be able to properly evaluate and validate the performance of these things to prove they're actually safe for large-scale use.
Because the real world is just so dynamic, so highly complex.
Mm-hmm.
You've got various roadways, street signs, pedestrians, other vehicles, buildings, everything interacting, plus unpredictable humans.
Exactly. And when you have that gap, between the ambitious forecasts and the messy reality of development,
You get the hype cycle.
precisely, those unmet expectations, they can lead to public skepticism, maybe more regulatory scrutiny.
So managing expectations, being upfront about how hard this actually is, becomes almost as important as the tech breakthroughs themselves.
Definitely. And to help kind of structure the progress, the U.S. Department of Transportation uses the SAE levels of driving automation, levels 0 through 5.
Right. Level 0 is, well, nothing. You're doing everything. Level 1 is basic driver assistance, maybe adaptive cruise control.
Yeah.
The car helps with one task.
One task, yeah. But you're fully in charge. Then level 2 is partial automation. The car handles steering and speed together, like some systems today.
And this is the key thing for level 2, right?
Yeah.
The human has to be paying attention.
Yeah.
Constantly. Ready to take over instantly.
Absolutely critical. Always. We'll get into the higher levels, levels 3, 4, 5, where the car takes on more responsibility a bit later when we compare, say, Tesla and Waymo.
Okay. So our mission here in this deep dive is to unpack your sources on this whole topic. We're going to dig into these multifaceted challenges, look at some cutting-edge innovations, and try to offer a balanced view on where things really stand.
Yeah, the goal is to really grasp the profound depth of this problem, especially that challenge of proving safety, like perfect safety across basically infinite, unpredictable, rare situations.
Okay, let's get into it. So the foundation of any self-driving car is its ability to see, right? To understand its surroundings.
That's the core, the perception system. It's the tech stack built on sensors and how the car processes all that incoming data.
And a really key sensor here is LiDAR. What exactly is that? Why is it so important?
LiDAR stands for light detection and ranging. Think of it like using lasers to build a 3D map in real time. Yeah, it sends out pulses of laser light and measures how long they take to bounce back off objects. Does this hundreds of thousands of times a second.
And that creates
what's called a point cloud. It generates these incredibly detailed three-dimensional maps of the surroundings.
Wow. A super detailed 3D laser map? What's the big advantage of that?
Well, the sources point to its remarkable precision. It gives you exceptional precision in mapping and object detection. It creates high-resolution images and maps, captures really fine details so it can spot smaller objects you need to avoid.
Right.
And another big plus, it's generally robust to tricky lighting. It's not fooled by shadows, bright sunlight, or oncoming headlights. Can even see through some things like fog or dust better than cameras sometimes.
Sounds almost like a superpower for the car.
Yeah.
But there have to be downsides. It sounds expensive.
There are definitely significant ones mentioned. Cost is a big one. Higher cost of equipment and maintenance makes it not very cost effective, especially for mass market personal cars, at least historically. It can also be vulnerable to interference from external light sources, maybe other LiDARs. And crucially, performance can really drop on rainy or snowy days.
Wait, rain and snow affect lasers.
Yeah. Raindrops, snowflakes, they can scatter the laser pulses, basically confuse the system, and sometimes its detection range is limited compared to radar.
Okay, so LiDAR. Amazing precision, 3D mapping, good in weird light, but expensive in struggles in heavy rain or snow. What about computer vision? Using cameras like our eyes.
Exactly. Computer vision uses cameras to see and interpret the visual world. It's a really reliable foundation for certain tasks like reading signs or traffic lights.
And this is where AI, machine learning, becomes absolutely fundamental, isn't it?
Oh, completely. AI and ML are what makes sense of those camera images. They power things like object detection and classification.
So not just seeing a blob, but knowing that's a pedestrian, that's a car, that's a cyclist.
Right. And understanding its size, position, how it's moving, even telling the difference between similar things like a motorcycle versus a bicycle. AI also handles lane detection, finding the lines, keeping the car centered, adapting to curves or faded paint.
And reading signs, traffic lights.
Critically important. Yeah, reading speed limits, stop signs, recognizing traffic signal colors and states.
How does the AI actually, learn to do all that from just pixels?
It's mainly through deep learning. These systems learn to assign specific features to objects to recognize them, and critically, to understand what's happening or what will happen based on the visual input.
It involves complex steps.
Yeah, things the sources call semantic segmentation. Basically, the AI figuring out what every single pixel in the image represents. Is it road, sky, car, pedestrian? It uses this to build a detailed understanding and teaches the car how to behave in a particular situation based on what it has detected.
What are the big challenges or limitations for just relying on cameras?
Well, cameras are inherently sensitive to the environment. Environmental sensitivity is the term used. They struggle significantly in low-light conditions, obviously can't see at night as far as it can in daylight.
And like LiDAR, bad weather.
Yeah, they struggle in rain fog, visibility just drops. There's also a really subtle challenge. Contextual interpretation.
Like what?
Well, the sources mention differentiating an actual pedestrian from a picture of a person's face on a sign or a bus advertisement. The AI needs to grasp the broader context, not just recognize a pattern.
Yeah, sounds tricky.
It is. And maybe the biggest hurdle for vision-based AI is the need for extensive and accurately annotated training data.
Meaning humans have to label everything in millions of pictures.
Pretty much. It's incredibly time-consuming, resource-intensive. Someone has to painstakingly draw boxes around every car, pedestrian sign, lane line.
Wow. Okay, so LiDAR gives precise 3D, but it's pricey and struggles in bad weather. Cameras are cheaper, great for signs, but struggle in low light, bad weather, and need mountains of this hand-labeled data. It really sounds like no single sensor is the magic answer.
Exactly right. The sources are very clear. Companies use multiple types of sensors to compensate for each other. Each has strengths, each has weaknesses.
And that's where sensor fusion comes in, bringing it all together.
Precisely. Sensor fusion is about integrating all that data from cameras, from radar, from LiDAR, using sophisticated algorithms.
It's not just about getting more data, though, is it? It sounds like you might get conflicting signals.
That's a huge part of the challenge. It's about overcoming the fundamental physical limitations of each individual sensor type. You need that combined system to be robust enough for safe operation in all sorts of messy, real-world conditions.
So if one sensor gets blinded by sun glare, or confused by heavy rain.
Hopefully another sensor, maybe radar or LiDAR, still has a clear view and can provide reliable information. Fusion aims to create a single, more reliable picture.
What are the main benefits when you get sensor fusion working well?
Well, it significantly enhances accuracy. It helps compensate for individual sensor weaknesses, and the sources claim it can reduce error rates by up to 90%.
That's huge.
It also helps reduce false detections, seeing things that aren't there, which increases overall system reliability, potentially above 99%. It leads to more consistent performance in adverse weather and low visibility than any single sensor could manage alone.
And faster reactions.
Yeah, by having this comprehensive, fused understanding of the environment, the AI can make more informed, timely responses, potentially reducing reaction times to under 100 milliseconds.
But even fusing all these sensors together,
yeah,
it's not a perfect solution yet. Still challenges.
Well, definitely not perfect. The sources point out challenges. For instance, sensors have different sampling rates, meaning data arrives at different speeds. They can provide conflicting information about the same object sometimes. You can still have false or misdetections or sensor blind spots where nothing has a clear view, maybe around corners or behind large vehicles.
And just handling all that data.
That's a massive one. Processing the vast amounts of real-time data from all these sensors simultaneously demands significant computational power.
Which can lead to delays. Latency.
Exactly.
Yeah.
Potential latency. Any delay, even milliseconds, impacts the system's ability to react quickly enough in a dynamic situation. The sources really highlight this processing power and latency issue as a substantial barrier.
Okay, so if we think about the car trying to see and make sense of the world, it's like its sensory system. It needs its own versions of eyes, maybe ears, a sense of space.
Kind of like how you use your eyes, your peripheral vision, your hearing, even your sense of balance all together, right? To figure out what's happening around you.
Yeah.
The car needs all its different senses, LiDAR, cameras, radar, working together perfectly in sync without lag to build a reliable understanding of this incredibly chaotic world. And getting them to do that flawlessly is just extremely difficult.
And just seeing isn't enough, right? The car has to figure out what happens next.
Right. Perception is step one. Then comes prediction, anticipating what other road users might do and planning its own actions.
Ah, prediction. That sounds, well, especially hard when dealing with humans.
It absolutely is. Anticipating human behavior is tough because, as the sources put it, humans are relatively unpredictable. ABs still struggle to reliably interpret pedestrians' gestures or human drivers' nuanced behavior.
Like what kind of behavior?
Like figuring out if someone is actually yielding at an intersection or trying to negotiate right of way in a complex merge. It's those subtle social cues that are hard to program.
Are there different kinds of prediction the car tries to do? Short-term, long-term?
Yeah, the sources talk about short-term prediction, looking maybe 1-3 seconds ahead for immediate reactive adjustments, and long-term, maybe 5-10 seconds or more, for more strategic planning, like preparing for a lane change down the road.
Any new tech helping with this?
Different approaches are being tried. Interestingly, the sources mention recent advances in large language models. You know, the tech behind things like ChatGPT are showing some early promise. They might provide valuable insights into nuanced human interactions that could improve prediction models. Still early days, though.
Okay, so prediction is about guessing movement and intention. What about the car knowing exactly where it is on the road, like down to the centimeter?
Right, that's crucial too, and that's where high definition or HD maps come in. These are way beyond your standard navigation map.
How so?
They are highly comprehensive representations of the physical world, capturing details with centimeter-level accuracy. Think of them as hyper-precise digital blueprints of the roads and surroundings.
Why are those so important if the car has all these sensors constantly scanning?
Because they provide a very stable, detailed reference. They're crucial for functions that demand real-time, reliable, and detailed environmental data, sometimes more detailed than sensors can reliably get on the fly, especially in tricky conditions.
Like poor GPS signal.
Exactly. They enable precise localization, helping the car know its exact position and orientation even when GPS is weak, like in urban canyons or tunnels. They integrate the road geometry, lane shapes, curbs with semantic info, speed limits, stop lines, crosswalks, and even dynamic data.
Dynamic data, like construction.
Yeah, temporary construction zones, accidents, lane closures, things that change day to day. The goal is to keep these maps constantly updated.
So they're like incredibly detailed safety nets and positioning tools.
Yeah.
What are the big challenges in using them?
Well, first, just building these maps initially is very costly. You need specially equipped vehicles to drive everywhere and gather that precise data.
And keeping them updated sounds like a nightmare.
It's a massive challenge. It's imperative to provide real-time updates because the real world is always changing. Roadwork pops up, signs change, detours happen, requires a huge ongoing effort. Plus, processing these large volumes of complex map data in real time, alongside all the sensor data, takes significant computational resources and advanced algorithms. And the initial map quality might be compromised if the mapping car encountered sensor limitations during data collection, like in bad weather.
Okay, let's try and connect this for you listening. Think about how you predict what another driver or pedestrian might do. It's often super subtle, right? Eye contact, body language, tiny movements, plus years of experience. Teaching a machine that intuitive prediction is incredibly hard.
Yeah. And then add the need for the car to know its exact position, down to the centimeter, using these hyper-detailed maps that themselves need constant real-time updating, even when GPS flakes out. These layers prediction and precise localization add just huge complexity on top of basic perception.
And these complexities really hit home when the cars leave the controlled test tracks and hit actual city streets. That's where the really hard problems pop up.
Absolutely. Which brings us to what people in the field often call the long tail problem.
The infamous long tail. What exactly is that?
It refers to all the rare but realistic events that happen out there. Things that don't occur often, but the car absolutely must handle safely if it does encounter them.
It's that saying, the last 1% takes 99% of the time.
That's exactly it. Think unforeseen types of accidents, really chaotic, crowded intersections, pedestrians behaving in truly bizarre ways, unexpected debris falling off a truck. The list is endless.
Why is that last 1%, all that weird, rare stuff, so incredibly difficult to train the AI for?
Because it's just extraordinarily difficult to predict all the conditions a vehicle might encounter. It's not necessarily a lack of total data. These cars collect petabytes, but the sources say there's no good way to understand where the edge cases are, hiding in all that data. You often don't know what you need to train for until you see it happen.
And the training itself is a bottleneck.
A huge one. It requires extensive data collection, curation, and labeling. But here's the kicker. Creating an annotated data set focusing on edge cases is where things get expensive and difficult.
Why? Because you have to find these rare events first.
Exactly. And then, even with smart tools, the most reliable annotation for these unusual situations still involves manual labor. People have to watch hours of footage, find that one weird incident, and carefully label everything that happened.
That sounds like finding needles in haystacks.
No, it really is. And this operational and economic burden means you can't possibly find and label every rare event. It severely limits the number of driving hours available for training AI models on these critical scenarios and restricts the AI's exposure.
So traditional AI struggles.
Yeah, approaches that learn patterns from common data suffer from the inability to generalize to unexpected situations they weren't explicitly trained on. If it hasn't seen something like it before, it might just freeze or do something unpredictable. It doesn't have common sense for novelty.
Wow. So it's the rare stuff that's not only hard to anticipate, but super expensive and time-consuming to even find and label for training, which fundamentally limits the AI's ability to handle anything truly new or weird in the real world.
Precisely. And we touched on human unpredictability and environmental issues earlier, but the sources really hammer these home as ongoing major hurdles.
Still struggling with gestures, yielding.
Absolutely. Predicting dynamic actions, intentions, interpreting subtle cues, negotiating right-of-way smoothly. Still big challenges because humans don't always follow strict rules, and the environment remains tough.
You mentioned sensors struggling, but what about specific examples?
Well, a really concrete one from the sources, lane markers can be covered by snow and not visible to the cameras.
Ah, right. If the camera can't see the lines.
Then the automatic steering function, which relies heavily on those lines, might disengage or fail. Sensor fusion helps provide some sense of position, but reliably figuring out the exact path without clear visual markers in snow, that remains a significant hurdle.
Okay, so given all this unpredictability, the difficulty with the long tail, the need for perfect accuracy, the whole validation and safety assurance piece must be absolutely immense. You can't just, hope for the best.
It's paramount. Sources state there's no margin for error. This is a life-or-death use case. Systems must be perfectly accurate. And they warn that the lack of proper validation will slow down deployment, period.
And you can't just test by crashing millions of cars in the real world.
No. Obviously, endangering the public seems impractical. So, the sources emphasize that alternate methods of validation are required. Things far beyond traditional road testing.
Like what kind of methods?
Things like massive scale simulation, running billions of virtual miles, using formal proofs, which are complex mathematical techniques to prove software correctness under certain conditions, and fault injection.
Fault injections,
Yeah.
deliberately breaking things.
Or kind of, yeah. You deliberately introduce faults, make a sensor give bad data, make a computer crash within the test environment to verify that the safety backups and redundancy systems actually work as designed.
Speaking of backups, what happens if a critical component does fail while the car is driving itself?
This is where fail operational design comes in.
Yeah.
It's a critical safety concept, meaning if a key component fails a sensor, a computer the system doesn't just shut down, fail stop, which could be dangerous mid-maneuver. Instead, it must continue operating safely long enough to bring the vehicle to a safe state, like pulling over to the side of the road.
That sounds way more complicated.
It dramatically increases complexity, cost, and the testing burden. To achieve fail operational capability, you need significant redundancy.
Multiple backups.
Yeah, often at least 3 redundant fail arbitrary components doing the same critical task. For the highest safety levels, sources even mention needing a Byzantine fault-tolerant system with 4 redundant components.
Byzantine fault tolerant. simply put?
It means the system can withstand not just components failing, but components failing in actively malicious or confusing ways, sending conflicting or wrong information. Designing and proving that these complex, redundant systems reliably detect failures, recover correctly, and ensure the failures are independent. That adds enormous expense and difficulty to the testing process.
Okay, this section really hammers home why this is taking so much longer than everyone thought. It's not just about the basic driving task. It's mastering the infinite variety of rare, weird events, handling unpredictable humans and environments, and then needing to prove, with near absolute certainty, that the system is safe even when critical parts fail unexpectedly. These seem like the biggest mountains still to climb.
And they are huge technical mountains. But beyond the tech, there are these really deep ethical and legal questions tangled up in all this too.
Right, like programming morality, the classic trolley problem, but in a car.
Exactly that. The sources are clear. AVs will eventually face unexpected driving situations, needing instant decisions to minimize harm. The examples aren't abstract. What should the AV do if a bicycle suddenly enters its lane? Should it swerve into oncoming traffic or hit the bicycle?
And the sources outline the different philosophical approaches being debated.
Yeah, they touch on utilitarianism, trying to maximize overall well-being, which might mean programming the AV to, say, choose to swerve and hit one pedestrian to avoid hitting 5 others. Research apparently suggests people often lean towards minimizing total harm.
But there are strong counterarguments.
Definitely. Grounded in what's called deontological ethics, which argues one human life cannot be weighed against another, every life is equal. From this view, an AV must not be programmed to weigh one human being against another. Follow the rules, don't make value judgments between lives.
Really complex territory. The sources also point out a fundamental limitation of current AI in these scenarios.
A really significant one. AI currently has a severe limitation here. It's generally incapable of adapting to new, unplanned situations from an ethical reasoning standpoint. Its response is limited according to the finite number of tasks it has been trained on. It doesn't have human-like intuition or generalized ethical judgment to handle every possible life-at-risk variation it hasn't seen before. The sources suggest the ultimate goal should be avoiding accidents in the first place, which is obviously true, but highlights that AI struggles to reason ethically like humans might in truly novel, high-stakes situations.
There's also the worry about algorithmic bias creeping in.
Yes, a major concern. If the AI is taught to use prejudiced data, maybe data reflecting historical societal biases, then it can make discriminatory decisions.
Like potentially prioritizing the safety of certain groups over others.
That's the risk. The sources stress it's critical to identify and diminish potential biases in the algorithms and the data used to train them.
And then the massive legal question. If an AI makes a split-second safety decision, who is responsible when things go wrong?
It's incredibly complicated. The sources list a whole range of potential parties. The company operating the EV service, the vehicle manufacturer, the providers of the software or sensors, maybe the human driver if they were supposed to be supervising, or even the programmers if bias is involved.
And the lack of clear regulations, especially in the US, makes this even harder.
Significantly harder. There's no unified federal regulatory framework right now. It's often a patchwork of state-by-state rules. Existing fault-based insurance frameworks were designed assuming a human driver is in control, making them ill-suited for deciding liability with autonomous systems.
Creates a lot of uncertainty.
Massive uncertainty, significant uncertainty for courts, manufacturers, drivers, and insurers. It's tough to judge algorithmic negligence when the rules aren't clear. This legal fog is noted as an impediment, holding back innovation and investment because companies fear unpredictable liability.
How are people thinking about solving this accountability puzzle?
It's complex. Ideas like giving AI electronic personhood are floated, but there's worry about creating convenient scapegoats. The focus seems to be shifting towards demanding much more transparency and traceability in how the AI makes decisions.
Like an audit trail.
Exactly. Accountability trails, so investigators can understand why the system made a particular choice. It looks like a multi-layered approach is likely needed. Maybe new liability frameworks, stricter transparency requirements, mandatory insurance schemes, and ethics boards. Some have even proposed things like victim compensation funds.
But maybe the biggest hurdle stopping people from jumping into robotaxis tomorrow, according to the sources, isn't the tech or the law.
That's a fascinating insight from the research cited. It suggests the ethical dilemma as the most significant challenge to overcome for public adoption, even more so than any of the technical or legal challenges.
Really? More than the tech?
Apparently, people are most concerned about the potential risk that ethical dilemmas can pose when they think about self-driving cars.
So it boils down to trust. These ethical worries are the primary psychological barrier stopping people from fully accepting this technology.
That's the argument presented. Even if the car drives perfectly 99.999% of the time, if you, the potential passenger, don't trust how it will handle that 1 in a million unavoidable crisis, you might not get in. This makes sorting out the ethics not just a philosophical exercise, but a commercial imperative.
Yeah. This whole section really underscores the human dimension. Can you, sitting in the back seat, trust this machine to make a profoundly moral choice in a fraction of a second? Who pays if it gets it wrong? And can you trust it's not biased against you? These deep ethical questions, the sources suggest, might be the biggest roadblock to public trust right now.
Yeah, absolutely. And to see how these fundamental tech and ethical challenges play out in practice, it's really useful to look at how two of the biggest players, Tesla and Waymo, are tackling them with very different strategies.
They really do have divergent technical philosophies, don't they?
Fundamentally different. Tesla, as the sources describe it, primarily uses a camera-only approach, Tesla Vision. Their system is SAE Level 2, partial automation, always relying on the human driver as the backup.
And their philosophy
is basically to train the car, similar to how humans drive based on what we see, using just visual input. They're pursuing what's called an end-to-end AI strategy training, a single neural network to drive directly from video.
Which is harder.
Considered a lot harder by many in the field because you're asking one AI model to figure out everything, perception, prediction, planning, just from cameras. Limiting the input sensors makes robust perception in diverse conditions tougher and requires the AI to learn incredibly complex representations from less raw data compared to using multiple sensor types.
Okay, and Waymo takes a different path.
Completely different. Waymo uses multiple sensor modalities, LiDAR, radar, camera, a whole suite of sensors.
Giving them more data, more redundancy.
Exactly. The goal is a comprehensive view, redundancy, and sensor diversity to compensate for the weaknesses of any single type. They operate SAE Level 4 robotaxis, that's high automation, designed to handle all driving tasks within specific conditions without needing human intervention.
And their software approach
is more modular. They use a series of neural networks trained separately for different tasks, designed as a generalized solution that they hope can eventually work everywhere and on any vehicle platform.
Okay, so big picture. Tesla is cameras only, single AI brain, Level 2 needing human oversight, trying to mimic human vision.
Waymo is multi-sensor, modular AI, Level 4 aiming for full autonomy but within defined areas.
Right. And those different approaches lead to very different operational strategies and real-world challenges.
Waymo operates in specific zones.
Yes, their L4 robotaxis operate within defined operational design domains, or ODDs.
Yeah.
Typically geofenced, highly mapped urban or suburban areas where they've done extensive testing and validation. They're quite cautious. They won't just turn the system on in a new city if their safety criteria aren't fully met. And their cars are designed to be fail operational.
Yes, that's key for Level 4 without a human backup. If a critical component fails, the system is designed to maintain control and bring the vehicle to a safe stop by itself.
Whereas Tesla's L2 FSD is designed for much broader use, basically anywhere, but always with the human driver as the safety net.
Correct. It relies on the human driver as the fail-safe, who must be ready to hand over immediately if the system encounters something it can't handle.
Which puts a constant burden on the driver.
It does, and sources note this can lead to problems like over-reliance, complacency, and reduced situational awareness. Drivers might trust it too much.
And the marketing, full self-driving, has drawn criticism.
Yeah, safety regulators like NHTSA have criticized that branding, suggesting it could give drivers a false sense of security, create a responsibility gap, and potentially contribute to misuse or incidents. Anecdotally, some drivers also report frustration with the system being overly cautious sometimes, or giving frequent alerts requiring them to intervene.
And the key point here is that despite these very different tech stacks and operational models, both companies have faced significant safety incidents and regulatory scrutiny.
Absolutely. It really underscores that the core challenges dealing with edge cases, validation, real-world complexity are industry-wide problems, not specific to one approach.
Can you give some examples from the sources? Tesla first.
Sure. NHTSA has investigated numerous Tesla Autopilot FSD incidents, including crashes in reduced visibility conditions like sun glare or fog where cameras might struggle. A fatal accident involving a Tesla on FSD hitting a pedestrian was mentioned. Tesla's had major recalls affecting millions of vehicles related to Autopilot and FSD software.
I like the one where NHTSA cited unreasonable risk for the system failing to adequately adhere to traffic laws.
Exactly. Plus, studies cited in the sources link driver distraction and over-reliance on these L2 systems to some incidents.
And Waymo, even with its cautious L4 approach and multiple sensors, isn't immune.
No, they've had incidents and recalls too. Recently, May 2025, a recall for over 1,200 vehicles to update software after collisions with stationary objects like chains, gates, and other roadway barriers. 16 reported incidents, thankfully no injuries mentioned there. They had earlier recalls too, related to predicting how towed vehicles might move, and one instance of striking a wooden pole. And NHTSA opened an investigation into Waymo in May 2024.
Why?
Citing reports of driving behavior that potentially violated traffic safety laws and collisions with clearly visible objects that a competent driver would be expected to avoid.
So the fact that both these major players, leaders in the field with such different philosophies, are facing recalls, investigations, and dealing with real-world incidents.
It really drives home that the fundamental challenge of achieving near-perfect safety and validation across the immense, unpredictable range of real-world scenarios is an industry-wide hurdle. No single tech approach has completely solved it yet. It's not just about one company's specific choices, it's about the sheer difficulty of the problem itself.
Right. Seeing how Tesla and Waymo grapple with this, different tech, different strategies, different levels of automation, really highlights the trade-offs and the immense task everyone faces. Their incidents, while different, underscore that getting this right, safely, at scale, remains a massive unsolved challenge for the entire industry.
Yeah.
So, wrapping up this deep dive, the big takeaway is pretty clear. Self-driving car development has turned out to be way more complex and protracted than initial optimistic projections.
Definitely. The core difficulties really are that immense real-world complexity and edge case complexity, especially that stubborn long tail of rare events. And combined with that, the non-negotiable need for perfectly accurate systems, no margin for error, which demands these incredibly difficult new validation methods.
And the key technical hurdles we talked about. Sensors having limits, needing robust sensor fusion that isn't perfect yet. The struggle to predict unpredictable human behavior. Environmental challenges like snow covering lanes. And that huge cost and effort involved in finding and labeling data for the long tail.
And then there are the societal hurdles, those persistent ethical dilemmas around unavoidable accidents, the potential for algorithmic bias. Plus, that fragmented legal and regulatory landscape creating so much uncertainty about liability.
And maybe most importantly, what the research suggests. That public trust, largely hung up on concerns about those ethical dilemmas and the risks they perceive, is actually the primary psychological barrier holding back widespread adoption right now.
But, despite all these massive challenges, progress is being made. Innovation continues. We see advances in sensors, better LiDAR, cameras, radar. Deep learning keeps improving. Sensor fusion algorithms get smarter. HD mapping gets better. Simulation platforms become more sophisticated. And there is research focused on ethical algorithms, primarily aiming for accident avoidance.
Still, that long-tail problem and the sheer immense validation burden required to prove safety, those seem to be the fundamental reasons why the timelines have slipped so much.
Absolutely. Future progress looks like it will be incremental, data-intensive refinement, just grinding away, proving safety for more and more of those complex edge cases.
So what's a realistic outlook based on the sources? When might we actually see widespread deployment?
The projection is that mainstream L45 deployment will be slower than once anticipated. For personal cars, Level 2 and maybe Level 2 Plus systems are expected to be the dominant form of automation for probably the next decade.
And robotaxis, like Waymo.
L4 robotaxis might expand, maybe to 40 to 80 cities globally by 2035, but likely concentrated in specific, suitable areas, primarily in places like China and the US to start, still operating within defined domains.
So the path forward isn't just about engineers building better tech in a vacuum.
No, not at all. It requires a really multifaceted approach, what the sources call a comprehensive societal contract. We need continued research, yes, especially into things like social intelligence for AVs and better validation methods.
But also collaboration.
Crucially, collaboration across technology, ethics, and policy. It's about building public trust, advancing technology, ensuring regulatory alignment, optimizing business models, and fostering industry collaboration. Policymakers, ethicists, technologists, everyone needs to work together to craft accountability structures that society can actually trust.
Okay, so considering all of this complexity, the immense challenge of the real world, the difficulty of the long tail, the current limits of AI in generalizing ethical reasoning for novel situations, and crucially, the finding that public trust, rooted in these ethical concerns, is the biggest barrier. It leaves you wondering, doesn't it? Perhaps the future of autonomous vehicles rests less on just refining sensor fusion or algorithms, and maybe more on first crafting a broad societal consensus about how we value human life and assign responsibility when unavoidable accidents happen.